think we have some form of control still, making our constant binary choices and voicing our equally shallow opinions more loudly or quietly. Most people can't even decide what color to wear or which burger to eat. What the does it matter, man? Autonomy is an illusion. Autonomy is an illusion. Autonomy is an illusion. Most people can't even decide what color to wear or which burger to eat. What the does it matter, man? Autonomy is an illusion. Autonomy is an illusion.
Find your way into this wonderland. Cross the maze, the dark, the innocent. Chase the faith, the thrill, the heaven sent. I got you wild upside down. The labyrinth will guide you far away to a place where senses will decay. Your ghost and mind will shadow play. I got you wild upside down. Upside down. Find your way into this wonderland. Cross the maze, the dark, the innocent. Chase the faith, the thrill, the heaven sent. I got you wild upside down. The labyrinth will guide you far away to a place where senses will decay. Your ghost and mind will shadow play. I got you wild upside down.
Sometimes I have to keep on breathing in. My lungs are filled with too much pain. All the shadows of the past that I'm so leaving, they held me in my sleepless nights. And I'm drowning in the noise like a free fall. Walking along my path for too long.
crazy, berserker. I killed it, it's murder. Go 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 crazy, berserker. Crazy.
It's 7 o'clock. Okay, I want to thank everybody for coming here tonight, and everybody that's out there watching the live stream. I want to welcome you to this session. We are in chapter 4 or module 4 of the ARRL book, and tonight we're going to be talking about propagation. As you know, last week, we talked about the components and how we use the components to mess around with the electrons and turn them into power. Well, tonight we're going to talk about how we're going to get that power out of the radio, up the coax or open line wire, and all the way up to the antenna, and then make it propagate throughout the world with the electromagnetic waves. Basically, radio propagation, getting from point A to point B. It's really just that simple. The radio waves, they go out into the air in a lot of different ways, and a lot of it just depends on the frequencies they're on. A lot of it depends on the terrain. The environmental thing, whether it's rainy out or not, will affect the radio waves a whole lot, and we're going to be going through all that tonight. The radio waves go out there basically in 3 different ways: the line of sight, ground wave, and sky wave. We're going to talk about each one of these 3 separately. The first we're going to talk about is line of sight. Most people are familiar with line of sight. It means if one antenna can theoretically see the other antenna, you can have good radio communications. In the VHF frequencies, the lower UHF frequencies, this radio wave can bend just a little bit, so it can go past the horizon just a little bit. But normally that is line of sight, is when one antenna can see the other one. There is some attenuations, of course, when the radio waves is going out into space. That is on all the frequencies. Now, the propagation mode mainly for VHF and UHF. VHF is from 30 to 300. UHF is 300 up. Got to know that for the test. Anyway, VHF and UHF is mainly line of sight stuff, but the signal will bend. To give you a good example of this, when the ship I was on was going into Pearl Harbor, we were trying to call the harbor master at Pearl Harbor, Hawaii, so they could have a tugboat ready for our ship to, push us up to the dock and all this stuff. Our ship couldn't get a hold of the harbor master. It was on VHF frequency in the 200 megahertz range. They kept turning up the power and turning up the power and turning up the power. They still couldn't raise Pearl. I came up with a bright idea: turn the power all the way down. They turned it down to about 10 watts from a maximum of 200 watts. They went down to 10 watts, called them and got them on the first try. The reason being that radio wave wasn't that strong, and it was bending on the earth. Before, when it was so much power, that signal was going out line of sight, and it was literally, with the curvature of the earth, it was shooting way over the top of Pearl Harbor. But we lowered the power down, the radio waves started to bend with the earth, and that's when we got communications. So line of sight, it is line of sight, but you must realize it can bend to extend that across the horizon just a little bit more. The ground waves. Ground waves are the ones that you use to talk locally. And by ground waves, we're talking maybe a couple hundred miles if we're lucky. It's the radio wave that, when it comes out of the antenna, it hugs the earth, and it travels the current miles. Don't go near as far as you can when it goes on skip. The range is a few hundred miles on all the bands used by amateur radios operators. So it doesn't matter which band you're on, whether you're 20-meter band or 10-meter band, 40-meter band, the ground wave sticks to the ground, and it sort of peters out after a while. These radio waves, when they're going through the air, they can refract or diffract. Now, reflect is just like a pool ball bouncing off the side of a table. It hits it, and it goes off at the same angle. Refracting is just a little bit different. The reflecting, by the way, it reflects off of water, steel buildings, that kind of stuff. The refraction is a bending of the signal. It bends around stuff. Anything can cause it to refract the ion, cause it to bend. We will be going over the ionosphere in some depth in a little bit later on. Another thing that it does is diffraction. You guys probably won't run into it around here. But if you're in the big cities, Chicago, where they got a lot of tall skyscrapers and stuff like that, you might run into this problem where you transmit with your handy-talkie, and the signal goes up and it hits the top of a signal on page 4-4, I think it is, or somewhere around there. They've got this slide, 4-2. If you're at home looking at your book, it's on page 4-2. That signal will go up there and it'll hit the top of the building, and it's called a knife edge. And what it'll do, that signal, most of it will keep going on up, but some of it will bend and sharply turn back down to the ground. You will have these areas right here, these shaded areas. If you're in a car in this blank area, you won't hear the signal. But if you drive just a little bit and get in this shaded area, you'll hear the signal. Drive a little bit more and it'll be blank, it'll be dead. And you go a little bit further and that signal will show up again. That's called diffraction, knife edge diffraction. The range on UHF and VHF signals, it does bend with everything, but you have to understand there is that difference between a reflection and diffraction. The diffraction is especially prevalent in HF frequencies. UHF signals penetrate buildings a lot better than the HF and VHF frequencies. On 9/11, in an after event report, the reason a lot of firefighters lost their lives was because they didn't have radio communications. The building, they were up so high with so much steel girdering in between them and stuff, they didn't have radio communications with the outside world down on the floor. They didn't know the danger they were in. Unfortunately, it was too late. They were using UHF, but they were just so high up in the air with so much steel in between them, the UHF couldn't even penetrate that, and they didn't have good radio communications, and it cost them dearly. The buildings may block the signal, but with refraction, with bending, you can bend your signal and they'll go around the building. You'll block it if you're going head on, but it will bounce around and go around the signal that way. We don't run into that much down here because we don't have that big of buildings down here to really be with that. Now, if you're, I don't know, if you're out, standing outside of Menards or one of these buildings around here, you probably won't be able to talk, to the other direction if that building is in between you. But in the big cities, if you're trying to get into a repeater, a big ceiling may block your direct signal, but it may pick up your signal as it bends around those buildings and stuff. Picket fencing. Picket fencing you will encounter around here. When a car is out doing mobile and he's calling into the repeater to talk to you, for instance, his signal is going to be bouncing off of buildings that's along the roads and stuff, and it will be a picket fence effect. You'll get that kind of a sound coming through your speaker. That is picket fencing. Nothing you can do about it except get to a better position. Here in this area here, if you're going out toward Altamont, where you go up and down the valleys and gullies, you'll hear a lot of that going on, where you're losing the signal, it's bouncing off the metal buildings. You get a lot of picket fencing there. The troposphere, tropospheric propagation. The troposphere is what we believe we breathe in. It's the air down here on Earth. It goes up to maybe about 3 miles, or a little bit more, 30 miles, I guess. The radio waves in the troposphere will bounce around, and there's several different ways signals react in the troposphere. We'll be talking about those in just a little bit. The temperature inversions and weather fronts can form ducts and trap these VHF and UHF. And tonight we're going to be talking about a lot about VHF and UHF because as technician class operators, those will probably be your main operating frequencies. So you'll be seeing tonight, we'll be talking about VHF and UHF a lot. But if you notice this time of the year, you can notice tropospheric ducting, an example of it. You're out driving along out in the country and you see somebody's probably got a wooden fireplace going and their smoke is going up in the air. And it gets up about so high, and then all of a sudden it takes a right turn and starts going off horizontal. You probably saw it, maybe didn't notice it. There's the smoke going up, and it hits warm air, and then the smoke starts going horizontally. The radio waves do the same thing. It will be trapped in between this temperature inversion between a hot cloud, or hot air, and cold air. And that's what channels the signal for long distances. Tropospheric ducting. The ionosphere. This is where I think, in my opinion, ham radio operators have the most fun. working in the ionosphere. From a region about 30 to 260 miles above the Earth is where the ionosphere is. 30 miles, by the way, is considered the edge of radio space. You will be learning later on in this class, not this class, but in the next couple weeks, but the space, if you're above 31.6 miles up, you're considered a space station. It goes up to 260 miles. The International Space Station usually goes around to 250 miles. So it's up in the ionosphere, but it's in the very high reaches of the ionosphere. The upper area of the ionosphere, this way up in this area here, that is where the air is very, very, very thin. Few atoms up there of nitrogen, oxygen, and whatnot. And because there's very few, they can get ionized. And by ionized, it means they start making their own magnetic field. And just like a north pole of a battery and a north pole of a battery, repel each other, the radio waves will do the same thing. They'll go up there and they'll hit that ionized gases up there, and it will refract, not reflect, but refract back down. It will bend back down, and you will be talking here, say in Effingham, and your signal maybe will bounce London, England, Moscow, anywhere. The different levels. The different levels are because there's different thicknesses of the air, and they each are ionized differently. The more air you got, the more ionized it will be. The things you should know about it more than anything else is this ionization is caused because of solar illumination, sunspots. We will be learning in just a little bit about the sunspot cycle, how the sunspot about every 11 years goes in a complete cycle of sunspots. There will be a lot of sunspots, and then they'll peter off, and there'll be hardly any sunspots. And then there'll be a lot again. This goes over an 11-year cycle. Right now, we're at the cycle where the sunspots are just now going to start appearing again. And the reason we like a lot of sunspots is, you have to remember from your high school physics class, energy can't be manufactured or destroyed, but it can be changed, right? The surface of the sun, which is bright orange, a lot of power coming off of it. When a sunspot gets there, it goes to zero. It's a black spot. It's a sunspot. That energy had to go somewhere. Where did it go? Went out into space, it comes across the Earth, and that ultraviolet rays is what ionizes the spaces, all the different layers of the ionosphere. The sunspot cycle, it does depend on the intensity, the number of sunspots. The top of the sunspot cycle will be around 2024, I think it is. When that happens at 2024, if you guys are still just technicians, if you haven't upgraded to general by then, you guys get operated on 10 meters. And when you're at the height of the sunspot cycle, you'll be able to turn your radio on 10 meters, that's 28 megahertz, just above the CB band. You might call out CQ, and someone anywhere in the world may come back to you. It is really active when the sunspot cycles are so heavy. And that's when it gets really exciting, when you can go CQ and all of a sudden there's some guy from Australia answering you. And it will happen. It does happen. The higher number of sunspots, of course, makes higher ionization levels, and this is what we want as ham radio operators. The ionosphere, they call it an RF mirror. We've got several slides about this RF mirror. The ionosphere refracts. It does not reflect. It refracts. It bends the radio waves back to the Earth. The most refraction of amateur frequencies occurs at the F layer. The F layer is the very top layer. There's two layers, F1 and F2. During the day when the sun is shining on it, that F1 layer gets really ionized, and that's what your signal's bouncing off of. At night, when the sun is on the other side of the world, the ionization goes away, and then the F1 and F2 sort of joins together, and then you bounce off that combination of sections of the ionosphere. It depends on the diffraction here. If I can find it in your book for you folks at home, page 4-5. If you're over here talking, If you're on the right frequency, you'll go up there. It will be back, and it'll land over here in Europe somewhere. If your frequency is way too high or too low, if your frequency is too high, the radio wave will just keep going. It will not curve back down. If it's too low a frequency, your radio wave will just be absorbed by the F2 and F1 layers, and the other layers too, by the way. The skip wave, or sky wave, and that's responsible for all the over-the-horizon talking. HF frequency and low VHF. HF is the 10-meter band, 28 megahertz, right above the CB channels, and 6 meters, the 50 megahertz band. During the peaks of the sunspot cycles, those two are really hot frequencies. Really hot frequencies.
I'm out of sync on my end. Can pause for just a second here.
Sure.
All right.
Tonight we're also going to be talking about the feed lines going up. Take your signal from the radio on up there. We're also going to be talking about the antennas, different kinds of antennas. Not going into, in fact, break, you can take a look at. We've got some equipment like SWR meters, SWR analyzers, antenna analyzers. So we've got a lot to look at tonight to show you. But this very first, tonight we're going to be in 3 sections. This first section is just about propagation.
All right, should be good.
We're ready to go again. Okay, it is a mirror. Skip is very rare on 144 megahertz and higher UHF bands. You guys will be operating on 144, that's the VHF band, and UHF. Skip is very rare, but there is a phenomenon called sporadic E that your signals from 144 can go a long way. There is a repeater in eastern Kentucky that's on the same identical frequency that we are here in Effingham. And there are times when you can hear that repeater, a VHF repeater, from the eastern end of Kentucky, when normally a repeater will have, a standard repeater will have maybe a range of 50 miles, we'll say. Each ground to sky to ground trip is called a hop. And what's going on here is on the HF frequencies, you transmit your signal, it goes up to the F1, F2 layer, it bends back down, and it might hit in Ireland. It will hit Ireland and it will bounce back up off the ground and go up and hit the F1, F2 layer, and then it might come back in, who knows, Western Siberia. Each one of these things is a hop. In between these hops, you can't hear anybody. They can't hear you. But in Ireland, they could hear you, and in Eastern Siberia, they could hear you on each separate hop, like that. It's good to know that because a lot of the times you'll be getting ranges that you'll just find phenomenal. How were you talking? Yes, sir.
On the hop, it affects who you hear and who you receive. I just stay on the same frequency as the guy you're talking to. And you start, I'm going to talk to you, okay?
Yeah.
It hops.
Yeah.
I can't talk to you, and you can't talk to me. But how do I keep you on the line? We can talk.
Well, when it is hopping, we would be able to talk to each other. If the signal was hopping between us right now, these guys in the center couldn't hear us talking, but we could hear each other talking. Guys back behind me couldn't hear us talking, but guys over toward the high school, they would be on that maybe that second hop and they could hear us talking. So you can hear.
So do you wait till you're back? How do you?
It just happens instantaneously.
He's like you're talking to him, and somehow happens. There's nothing. Right on something wrong. I'm saying when you communicate.
It's two-way. Yeah, the hops are 2 ways, by the way. So if you can hear him, they can hear you. And fact is, if you're looking at your S meter and you want somebody to talk to, if somebody's coming in real strong to you, when you transmit, you will probably be coming in real strong to them. So it's a two-way street on that.
It's totally random, though, basically, right?
Pardon me?
It's totally random, though, really.
It's kind of random. Yeah. You'll find that at the end of the day, the skip, The ionosphere, the ionization takes place during the daytime. It starts around dawn and ends a little bit after dusk, because that's when the sun is up ionizing, the atmosphere. So this all happened during the daytime, and it was fairly steady. When you get to the end of the day, that's when you'll see signals. You'll be talking to somebody, and they'll be throwing like an S9 on your meter, and then they might drift down to an S2, real low, and they'll come back and forth and back and forth. That kind of fading you'll have. But during the day, it's usually pretty steady. There is a fluttering, distorted speech sound in CW when you're getting this irregular fading. Fading especially causes a lot of data errors on HF frequencies. A data error is basically if you're sending a data on the HF bands from here to there, and it might be a picture, it might be voice, digital voice you're going on, you'll get, because it comes in at from different angles, from fading and everything, it will have some errors involved. And with the digital stuff, usually, I think I can say this, that when you transmit a digital signal, it sort of also transmit a little guideline that goes with it. So at the receiving radio, it will note that if it's missing any of the initial information it needs. And if it's missing it, it will send a thing back to your radio saying, you got to send it again. There was errors in it. Into the digital stuff, you'll be learning, that's about 3 weeks from now, I think. We'll be talking more about how the digital errors appear and why they appear and how you can get away with them. The sporadic E. The sporadic E is in this area here. It's about 60 miles up to about 70 miles. It's in the sporadic E. And a lot of times, normally, this will be a 10, 6 meters operation, but normally you can only talk just 100 miles maybe. When the sporadic E is hot, when it's really ionized, you're going to get, you can have communications up to over 1,000 miles. So you get a really lot with that thing. Right below the E level is the D level. The D level absorbs a lot of radio waves. We don't, amateur radio operators don't even use the D layer to bounce signals or anything. It is so nasty, it absorbs it's the enemy. It absorbs our signals. The auroras is up north, the North Pole and South Pole. You get all sorts of, they call it a distinctive distorted sound. I've never heard it. So I'm assuming you got to be up to the North Pole or down to the South Pole before you really can find the effects of this. But that's called the aurora. Meteor scatter. When a meteor goes through the atmosphere, even though it's a tide, see, it makes that glow through the air and everything. That's ionizing all the ions, the atoms that are up there. And on 6 meters especially, I think they even, 6 meters, remember that because that's on a test question. At 6 meters, you can really use that meteor scatter. Short period of time, but you can talk phenomenally long distances with a meteor scatter. Basically, if both of the radios, no matter where they're at in the world, can see that meteor trail, you can talk to each other, kind of like talking to a satellite. Contacts up to 1,500 miles, they're saying you can do. So it's pretty far, and when you consider the power and everything, doing a meteor scatter is kind of exciting. It's very short-lived. I mean, if you get into the Pleiades meteor showers or something where there's a lot of meteorites coming through, you'll have a lot of activity on 6 meters. Okay, now we're going to go over some of the questions. They start at T3A01 if you're in your book. What should you do if another operator reports that your 2 meter signals were being strong, but now they're weak or distorted? What do? You just try moving a few feet. It's that simple. With your little walkie-talkie here in this building, I can stand here and get a signal into the repeater. I might come over here and it might go away. It's really that critical. So if you're talking to somebody and they say, hey, your signal's dropping out a little bit, that's all it takes, just moving a little bit. P3A06. What term describes this rapid fluttering sounds from mobile stations? That's the picket fencing. That's something you guys will come into. To help you get the question right, it's the rapid fluttering sound, and mobile will tell you that it's the picket fencing. Which of the following is caused the irregular fading of signals? And then is that the random combination of signals coming in? If you're sitting here and your antenna's up in the air and someone's talking to you, but they've got one of their signals came in this way, and their signals was bounced off of something else, they're coming in at the same time, they'll mess with each other. You can have all sorts of troubles trying to hear the guy, fading and all that kind of stuff. The data signals arrive via multiple pass, you will get error rates. And there again, you're on data, you might be just exchanging a picture, you might be talking voice, but if the two signals are from the same transmitters coming in at different times, it's going to have your large error rates, which means they have to resend the signal. And of course, which part of the atmosphere enables the propagation around the whole world? The ionosphere. Everything up. We got the troposphere that we live in, then there's the stratosphere, and then it goes on up from there to the ionosphere, and it's the ionosphere where our signals really start bouncing around the world. Why aren't direct UHF signals rarely heard on stations from outside your local area? Is because UHF signals usually aren't reflected by the ionosphere. They're all line of sight. So UHF will be line of sight. Now there again, the UHF signals have a tendency to bend with the Earth, but just a little bit, not a whole lot. The advantage of HF versus VHF and the other higher frequencies is, of course, it's the long distance ionospheric propagations is far more common than HF, far more common, because that's why we talk to everybody on across the sea. When you're talking to seas over station, you exchange QSL cards. They're now going a lot of electronic QSL cards, but the QSL cards are basically that you send this guy and he sends you one, and you verify that you talk to each other. You do 100 of them, and if you go to ARL, you'll get a certificate called the DXCC Award. So you can brag to everybody that you talk to more than 100 foreign countries. The aurora reflection, there again, that's the North Pole and South Pole. That's the rapid fluctuation of strength, and often the sound is distorted.
Yeah, quick question.
Sure.
Political barriers.
Yes.
Did you ever contact somebody like North Korea?
Not North Korea. At this time, I looked it up about 2 weeks ago. We can talk to anybody in the world right now. There's nobody that's got restrictions. North Korea. Their people talk to us.
So have you seen that?
I talked to Albania. Before the fall of the Berlin Wall, Albania was the most communistic country in the world. They opened up Albania, it was in the late 90s, I think. And I talked to them on the first month, and they were so excited there because finally the ham radio operators could talk to other guys around the world. But if the United States government, if the FCC says, oh, you guys can no longer talk to Iran, then we cannot talk to them. And we can't argue about it. We do not talk to them. But right now there is no restrictions to anywhere in the world where we can talk, but there are restrictions in the other part of the world of people talking back to us.
It's a self-governed deal, though. They can't actually stop us. It's just that you're not allowed to do it.
You're just not allowed to do it, yeah.
Isn't it possible you could inadvertently contact somebody?
Oh, yeah,
You don't really
sure.
know where this is going until you talk to them and know where
Yeah.
they are.
Because when I talked to the guy in Albania, it was a weird call sign, and that's why I went back to him. And it wasn't until after we got done talking that I looked it up and found out, hey, I was talking to a guy in Albania. Yes?
There is a list in your books. If it's not in the tech book, it'll be in the general book of the countries that are kind of iffy.
Yeah.
And the thing the thing that's important at that point is third-party communications. If you have somebody in your house that you're letting talk to another person, like you can't have a South Korean talking to another South Korean. They kind of
Right.
frown on that sort of thing, especially in native language. So there is a list of the countries that you really shouldn't conduct third-party communications with.
And it's not just political, too. Some of the countries, the government owns the telephone systems. So they don't want you talking free on ham radio operators to one of their missionary, for instance, you know. So they don't let them use the ham radio. They want them to use the telephone system so they can charge the long distance costs. It's a lot of political stuff runs into this. Yeah.
Are those people licensed who you're talking to
Most of them are, yeah.
through their own?
Yeah, through their own countries. Yeah, like if we go up to Canada, we do not have to get a Canadian reciprocal license. We've got that agreement. But if you go to other countries, if I would go over to, I think France, for instance, I got to get a reciprocal at France. I would have to go to their FCC, and they would issue me their class of license equal to the class of license I've got here in the United States. But yeah, everyone has to be licensed when you get on the air. Propagation types are mostly associated with occasional over-the-horizon signals on the 10, 6, and 2 meter bands. They're mentioning 10, 6, and 2 meters because that are the bands that you guys get to operate on. General class, extra class operators, we get a lot more of the bands to operate on. But these are the three of several that you get to operate on. Anyway, that's that sporadic E. That's when it's ionized really good. That's when your signals can go for a little over 1,000 miles on these frequencies here. Signals that's heard despite obstructions between the transmitting and receiving stations. That's knife edge propagation. And on 4.4, we go back to that knife edge propagation. Give you a little bit about the idea of it. If you're like up in Chicago, you might have your walkie-talkie, your mobile out, and you and the station that you're trying to talk to, the Willis Tower, Sears Tower might be in the way. Well, that way your signal will go up literally to the top of Sears Tower, and then it'll start splitting as it goes down. And if the other guy you're talking to happens to be in the good area, he'll be able to talk to you. He might drive a couple blocks and he'll lose you altogether. But that's sporadic. That's the knife edge propagation stuff. What mode is responsible for allowing over the horizon VHF and UHF of approximately 300 miles on a regular basis? That's tropospheric scatter. That's your signals, UHF and VHF, that are down here close to Earth. But they're going to be in about a 300 mile. You could talk to maybe, if you got a good power, you might be able to talk to somebody up towards Chicago, that kind of stuff. More realistically, if you got a mobile antenna, if you got a mobile setup, you can talk to base stations, maybe 20, 30 repeater stations, maybe 20, 30 miles away, which means that you can be 60 miles apart from another guy and you can talk to him with just a 25-watt radio because if the repeater's in the middle of you. So it works out pretty good with the repeaters. What band is best for communicating via meteor scatter? We're at T3CO7, and that is the 6 meter band, 50 megahertz band. The 50 megahertz band, 6 meters, that is right below the old VHF TV channels. Tropospheric ducting, that is the temperature inversion. It's cold down here on Earth like it is today, but you go up 4, 5, 6 miles, maybe a little bit more, 10 miles, and if it's warm air up there, your signal will go up and then it'll travel along that warm air to wherever you're going to be talking to. The best time for long distance 10 meter propagation via the F layer, that is from dawn to shortly after sunset. And it's from dawn for sunset because that's when the sun is up. And its ultraviolet rays are hitting the F layer, ionizing it, magnetizing it, if you will. And then your 10 meter band, which is 28 point something, 28.3 to I think 28.5 you'll be able to use, will go up there and bend and come down. And when there is a high sunspot activity, I'm going to say it again, you will be amazed. You might get on 10 meters and you might say CQ 10 meters, you know, like this. Somebody from anywhere in the world may be coming back to you. It's really a phenomenon that's really great. Why do VHF and UHF signals usually travel somewhat further than the line of sight? It's because the Earth does seem to make those radio waves curve a little bit. They don't go really line of sight solid like a light would be. A laser light is a straight line, you know, from here to there. But a VHF signal, it will curve a little bit to the horizon. Which of the following bands may provide long distance during the peak sunspot cycle? 6 and 10 meters. Those are two of your bands. And these are the long distance ones. The 10 is 28 megs. The 50 is the 50 megacycle band. Into 4. We're ready for 4B.
All right, give me a second. I'll get that pulled up.
And while we're doing that, getting it pulled up, if you'd like to
I get lost inside my thoughts, and when I start to think, oh, the Tahoe closest starts to end up on the brink. I tried so hard, but all these scars, they cut so deep I bleed. I fell so fast from heaven, it's like someone clipped my wings. Now I'm falling, and I can't see the ground. Can we stop this gravity? It keeps bringing me down. I can't breathe, and I don't wanna die. Can we stop this gravity?
In Battle Creek, I built a TV antenna and sent it towards Grand Rapids, which is northwest of Battle Creek. Christmas Day, about 1964, I turned on the TV in Channel 2. What's this weather pattern? It was a weather pattern out of Florida. We showed the weather broadcast, showed the state of Florida coming back in.
Okay, we're ready to go. Antenna fundamentals. Feed lines, which is going around, and probably one of the most misunderstood things in radio, the SWR, standing wave ratio. Antenna system. The antenna system is not just the antenna. The antenna system is the antenna and the coax and the feed line. Got to remember that right away. Basically what this antenna does, it takes this power, this 100 watts that's coming out of your radio, it's going up the feed line and it's going up to the antenna. The antenna then turns that 100 watts of power into electromagnetic waves. Now this 100 watts of power is 100 watts. You could light up a 100 watt light bulb. You don't want to light up a light bulb, you want to get it out in the air. So you run it up the feed line, go to the antenna, and the antenna changes that energy into the electromagnetic waves. It does just the opposite too. The electromagnetic waves coming through your antenna runs the signal back down through your feed lines. And the feed line, of course, just connects your station to the antenna. There's also, we're going to be talking about test and matching equipment. Testing equipment like SWR meters, antenna analyzers, that kind of thing. Some of the vocabularies when we're talking about antennas. An element. An element is the conducting part. The conducting part, it has to be metal of some kind, or receive the radio wave. This is the tape measure antenna. Go online, you can get dimensions for it. There's about 2 or 3 different kinds of these tape measure antennas. The different types have the spacing a little bit different. It is literally an old tape measure that you cut up into the certain lengths. Each one of these is called an element. It's part of the line. This middle one, keep you up to date, is the driven element. If you see here, the coax connects right into this driven element. That is the driven element. Went backwards on that. Boom, there we go. An array. Different kinds of arrays. If you're into business band and stuff, you might see an antenna on a police tower. A stick up and it's got, that's an array. Those are all radiating elements. The parasitic elements, this is the driven element. These are parasitic elements. This is a director. It makes a signal. Right now this antenna is radiating to the north, to our folks. This is the director. It tends to direct the signal north. This is a reflector. It's bigger. It makes the signal go that way too. Now, the way it does this is by self-induction. When this thing is transmitting a magnetic wave, this magnetic wave is cutting through this metal here. And we all know that when a magnetic wave goes through metal, it sets up a current. And if you have current in a metal, you have a magnetic wave. So it pushes forward. It combines some of the power that's going back, and it pushes it all forward. Same thing here. The electromagnetic wave that's intercepting this element is aiding the signal going north. So all your signals is going this way to the north. The director is a little bit shorter than the driven element, and the reflector is always bigger. You'll find out that in 2 meters, and it's on this PowerPoint somewhere, this length here is approximately 19 inches for 2 meters. And if you're wondering, I use this when we go fox hunting, and we'll be talking about fox hunting in a.
So the only one of those is hooked up to the coax.
Yes, just this center one here is the only one. The driven element is the only one that's actually hooked up to the coax here. And we'll be looking at this thing during the break. You'll be noticing this little wire here that looks like a dead short between the center conductor and the outer braid. It looks like a dead short, but it's not. To DC, it's a direct short. To AC, radio frequencies are AC. To AC, radio frequencies, it's not. But if you hook up an ohm meter to it, it would show the thing shorted. The feed point is this point here, where the coax is literally hooked up to the point. Every antenna will have somewhere where there's the actual feed point. Sure. Here's the feed point. The coax, this thing would be like hooked into your walkie-talkie, comes up the coax, the center conductor goes up to there, the shield or the ground goes down to this one. Element. Radiation. This is something you just need to know about. You probably won't hear about it much, but a lot of people, if you're talking to people and you're talking about your antenna radiating out, a lot of people think radioactivity. These things radiate electromagnetic waves. They do not radiate waves. It's radio waves. These electromagnetic waves, they are electric and magnetic fields at right angles to each other. If this is a sine wave, right? Electrostatic sine waves. The other part of a radio signal is the magnetic waves. They are like this. They're at right angles to each other. You've got the electrostatic waves, and then you've got the magnetic waves. We'll learn in just a little bit that the antenna, it will be either a vertically or a horizontally poised antenna. Spread that, and it's by the AC, and I want to emphasize again, it says by AC current, RF is AC. A lot of people, when they hear AC, they think of 60 cycles. Well, we're way above that. We're up into 7 million cycles, 14 million to 60 cycles on the current. The polarization. Right now, this antenna is vertically polarized. We call it vertically polarized because the driven element is vertical with the earth. Now it is horizontally polarized. Vertically, and then it goes horizontally. Now if you look at the radio static waves, they're like this because it's vertical. If it goes horizontal, the electrostatic waves go like this. And remember that I need one more hand. They're like this, so if it's vertical, it's like this. The magnetic waves are horizontal. And kind of the way it works, if you want to visualize it going through the signal, the receiving antenna has to be the same polarization for it to really work good. If you've got this thing vertically polarized, you want to talk to another antenna that's also vertically polarized. If you have it like this is called cross polarization. Doesn't work well at all. You want them both the same kind. There was a FM radio dealer in the woods that was selling FM radios to farmers. farmers that he could save them $800 because if you buy a FM radio license to get the licensing company to get your license, you'll spend around $800. But anyway, he was saving him $800 by putting him on his frequency. Into is all the farmers. He showed talk, and it was a mess. What one farmer did, he took all of his antennas, instead of vertically polarizing them, he put his horizontal sideways. They weren't mounted on the top. He eliminated all the other people from interfering with him, even though they were on the same frequency. This is the idea of antenna polarization. Repeaters you'll be talking into are all vertically polarized like this. The walkie-talkies, this one is vertically polarized. If I was talking like this, to talk to this antenna any distance off, I would have to put this antenna horizontally polarized too.
Now, that's something that I wish some people
Yeah.
like on portables working, because I don't know how many times you might lay your portable down.
Uh-huh.
You're talking on a remote mic, and that's just totally, your signal's messed up.
After you guys really get to experience this, it's going to bug the devil out of you guys when you watch guys on television and movies. They're always cool when they talk on their handy talkies. 10-4, they're holding them horizontal when they should be holding them. Doesn't look near as cool with a vertical antenna right up there. But you'll know, here when we got first got the 900 megahertz here in Effingham County, some of the deputies were complaining about that. They weren't getting into the repeater. Come to find out, they were used to talking like this. And the simple adjustment of going like this made all the difference in the world.
The other thing you'll notice from time to time is nobody told the people at Walmart and Rural King that you can't talk into your hand.
Yeah. If it's classified as a vertical or a horizontal antenna, as defined by the way the antenna is, vertical or horizontal. On the HF bands, when you're talking around the world, you'll be using horizontal. You might not have a big array like this thing, a Yagi antenna, but even if you've got just a dipole antenna, we'll go over that in this next section, but it'll also be horizontally polarized. The combination of polarization is called elliptical. This happens in two occasions. First of all, when you're talking skip on like 10 meters, if it's going real good, when your signal goes up there, it will have a tendency to twist going up there. It won't stay straight, vertical or like this. And this is called elliptical when it starts doing this stuff. If you're doing any satellite work, which you guys would be allowed to talk on satellites, you've got the frequency privileges for the ham satellites going over, they spin as they go around. And as they go around, the same reason the bullet spins, keeps them sort of in a straight line. But those are the two elliptical you'll be running into. The cross polarization, this is where you have to keep both antennas the same polarization, both vertical or both horizontal. When you're fox hunting, like I said, I use this fox hunting. As you get closer and closer to the fox, the guy sitting out in his car somewhere transmitting, he'll transmit for 1 minute and then he stays silent for 4 minutes. He's on for 1 minute, off for 4. And when he's on the air, that's when you're trying to figure out where the devil is at. When he's off the air, that's when you drive from spot to spot. See? But anyway, yeah, when you get up close to him, the signal is so strong that your S meter is just full strength all the time. So what you can do, I turn this thing sideways and it cuts his signal way down, and then I can get a better idea of where he's at. We will be having a fox hunt here later in spring, and if you guys haven't been on a fox hunt, you've got to do it. It's a lot of fun. Basically, one guy will go out into the county somewhere. He will be on public property, and he will sit there. He will either use a handy-talkie or his mobile, and he will transmit for 1 minute, off for 4. And while this is going on, the various fox hunting teams are spreading all around trying to figure out exactly where he's at. It's a lot of fun. The guy that spends the least amount of mileage getting to him is the winner. And believe me, you can put on, around here, everyone will put on around 25 miles maximum. So it's not that much of a driving, but it's a lot of fun for a Saturday or Sunday afternoon. You get to see parts of the county you'll never ever see normally, but it's a whole lot of fun. It's called fox hunting. Of course, you guys will all be notified when there's a fox hunt going on. Ride along. That's how you learn how to do the fox hunting. You'll probably ride along 2 times, and then you'll get the bug. And you'll be going on the internet and figuring out how to build this antenna. This antenna, by the way, if you build one of these, it's super easy, like an old tape measure. Put on these little plastic water lines, because if you get out in the air, any kind of wind, without those, the thing will do like this, and it's no good for hunting at all. So I put these little plastic things on there just to keep these elements nice and stiff in the wind. Just a little thought. It says it can reduce the effector by 100. So you can tell that by just changing the position of your antenna from horizontal up to vertical or vice versa, you can really cut down on the reception. The elliptical polarized waves, such as the sky waves that are bending like this, you don't have to worry about polarization that much. It's going to pick them up. If it's vertically or horizontally polarized, it won't be as good as a reception as if the signal was a solid vertical or a solid horizontal. But it is elliptical, so it doesn't really matter that much of a difference on your antenna on the polarization. The decibel. A decibel is a way to measure things, period. 10 dB log, 20 dB log, positive dB range up there. These things right here, don't worry about them. It's too confusing. If you're going to study electronics, yeah, you'll get into it. But what you will want to know, why you want to know a little bit about dBs, is because of antenna gain. When you buy an antenna, it will say it's got a 3 dB gain. It might have a 6 dB gain or a 12 dB gain. And what these is if this was a can of water right here, a cup of water, if I have a container over here that's got 2 cups of water, it is a 3 dB gain. It's twice as much. 3 is the magic number in dBs, by the way. 3 means you've either doubled your amount, or if it's a -3, it means you went half. Instead of a full cup, you went down to a half a cup. That's a -3 dB. It doesn't, it's just the amount, it's just an amount is what these dBs are. It's a reference amount. So if you have a cup of water, then all of a sudden you increase it up to 2 cups of water, you've had a 3 dB gain in amount of water. If you increase this up to 4 glasses of water, then you'll have a 3 dB gain and another 3 dB gain. You'll have a total of 6 dB gains. 3 is the magic. 3 means, at 3 it means you've doubled your power, or if you've got a -3, you've halved your power. You've cut your power in half. The gain of the antenna. Okay, I said, you want to buy an antenna that's got maybe a 3 dB gain. The scientists, these antennas, they figured out that if you have a 100-watt radio, you put it up into just a little dipole antenna, simple dipole antenna. And if somebody was over at that side of Illinois or something, and they pick you up, right? Now, if you've got an antenna that has a 3 dB gain, that means that that guy over the other side of Illinois thinks all of a sudden now, instead of a 100-watt transmitter, you've got a 200-watt transmitter. It's all in the amounts. It's not any numerical values as much as a amount or a volume of power, the 3 dB gain. So a 3 dB gain antenna is good. It means that the guy you're talking to thinks you've got twice the power that you actually have. Isotropic, that is the equal radiation in all directions. If you've got an antenna sticking up here in the air like this thing, it's going out equally in all directions. It's going out this way, it's going out this way, all directions in the same direction. If it is, however, an omnidirectional, then it's talking about the horizontal. It's going out this way, around this way. This particular antenna is pointed east right now. It's directional, it's a beam. An omnidirectional one, it would be pointing in all these directions. In fact, if I would just have this thing by itself without these directors on it and transmit, this antenna would go out equally in all directions. It would be omnidirectional. When I put these elements onto it, then it makes it a directional beam antenna, and it sends all the power, theoretically sends all the power in one direction.
It's also the reception.
Yes, I'm glad you brought that up. It works both ways. Not only will this thing receive a signal from that way a whole lot better if it's pointed that way, if it's pointed this way, it might not receive it at all. But it is directional on receiving and transmitting, yes.
On gain, is that solely though on transmission?
No, it's both ways. Both ways. Mm-hmm.
That's good for point-to-point transmission. Vertically polarize that, you want to cause stripping to another thing, it's good for point-to-point transmission also.
And then, of course, directional, like I said, the directional means the signal is going that way strong, and it's picking up the signals from that direction a lot better. Radiation patterns. Somewhere in your book, on page 4-8, you'll see this pattern right here. If you're up on top of the antenna, up in the world about, 100 feet up in the air, and you're looking down at your antenna, this is a directional antenna. It's pointed, it's going this way, might be to the east, just depending on where you're looking at here. The line is how strong it is. With a directional antenna, you're not getting any power off the back end of it at all. This is 180 degrees, this would be south. North, however, you're getting full strength. It doesn't really matter if this is wattage, how many wattage, it's the maximum strength you're going to be getting. And as you can see, it slowly comes down to nothing. So when you buy an antenna, you might get one of these with it to show you. If you got a beam antenna, you might get one of these things, and it'll show you about how this beam spreads out when you want to talk to them. And there's different, they're all not like this kidney beam. There are different ones. We'll go in those in just a little bit. It is calibrated in dBs. Radiation pattern, the nulls. The nulls, if we go back to this one, I think there's one ahead of it. No, we'll go back. If you're looking at that table, that graph, the null is the, dadgummit. This is the null here. There's no power going out there at all. This would be one of the nodes, a node. This thing can have more than one node. This one node is pointed this direction. But the null is this area here where there's minimum gain at all. The main lobe is that highest strength going, I wish they had these all together. This is the main node going out this way. This is the maximum power going out this direction. The side lobe is any other lobe other than the main lobe. Some antennas, you can talk real good that direction. You can also talk pretty good that way and pretty good that way. This way, not so much. These are side lobes, and that's the main lobe. And the forward gain is basically how much stronger the power is going toward where the antenna is looked at. There's the azimuth and elevation patterns. If you're going to talk skip, and you got these beam antennas up in the air, it's good to know these two things. The azimuth is basically what direction you're pointed in, whether you're pointed south, east, north. That's the azimuth of it. The elevation pattern is this thing here. Because if you look at the pattern on the Earth, if this was the Earth, and then this is let's call this the F layer up here. Depending on where you actually point your antenna, what angle you point the antenna, your antenna could go straight up here and bend down here. If you make it a little bit shallower of an angle, your antenna would come out this way and land way over here. That's why the azimuth, or the elevation is so important. Most guys on their antennas at home, when they got the beam antennas, are just strictly flat, even, right? But the guys that are really into ham radio and really like doing skip, they will put a rotor on it that will turn the azimuth, where they can point the antenna. They will also put another rotor on it where they can lift the antenna to get the different angle so they can hit the ionosphere and hit these different loops. Yep. Okay, this one here is this elevation pattern where you raise and lower the antennas up and down like this. As you can see, these are the main, let's wait till he gets the light off. On this thing right here, these are the two main lobes. They're the two strongest ones, so they're the main lobes. They've got another pretty strong lobe going up this way, but it's not as strong as these two, so it's considered a side lobe. And there again, this guy knows his antennas. He knows that his signal is going to be going out this way and landing way over there. His signal will also be going over that way and landing. So he's going to be hitting two sides of the earth at the same time. This side lobe that's going straight up, more than likely it's going to cut right up on through F1 and F2 and go into outer space. The front to back ratio is basically, again, in dBs, and it's how much power is going out the front of the antenna as compared to the power that's going out the back end of the antenna. So you want to having that on your, you'll have that all that on your specs. You'll know that, and you'll have the side ratio is the same thing. It will tell you how much power is going out to the front, and then how much power is going off out of the side antennas too. Because even though we say it is directional, we say that this antenna is pointing that direction, a lot of the signal will still be going out in this direction. You'll have a very wide pattern. That's why when you're fox hunting, you'll be doing this with your antenna. You'll be going through the entire lobe, trying to figure out where it's the strongest at, and when you get where it's the strongest at, that's when you can take your heading off of a compass or something and figure out where he's at. Feed lines.
That's basically the whole concept of the triangulation.
That is exactly it, triangulation.
So if you've got two guys who are in communication with each other,
Yep, we're
they're
gonna.
using this, and one shoots one azimuth, and another shoots another azimuth, those intersecting points where you're.
You got it. Yeah.
So you can team up and really.
Oh yeah. It's fun to team up, but it's more competitive when you know there's 4 or 5 of you all working separately, because you have to actually do more fox hunting then. When I'm doing a fox hunt, by my third shot, I will probably know within about a mile of where he's at, because the triangulation works. I will take a shot, and if it looks out according to the compass, I take a shot, you find out where his peak signal is at, receiving signal is at. I get out my compass, and I literally take a heading. And I've got my map of Effingham County. I put a line on. Then I might drive over 2 miles that way. So I'll be sort of aiming this way when I get him. I'll be taking azimuth reading, finding out his, the direction, put that on the map, and then they start crossing. There's been several times, and it's just by luck, I can't brag about this, it's just by lucky that, I've nailed a guy within about 50 foot on about 3 shots. When usually, if in 3 shots, if you can get him within a mile, you're doing pretty good. But I just happened to luck out. Feed lines. Okay, we passed that thing around with all the feed lines on it. I'm sure, hope you all had a chance to take a good look at it. The idea of the feed line is to get the power, that 100 watts from your radio, up to your antenna. There's some two basic feed line types. There's first the common coaxial cable. This common coaxial cable is used, you'll probably use it about 98 to 99% of the time. The next type, or the other type, is the open wire line. That's where you saw the twin lead. It looked like the old TV wire twin leads, and it had the window line a little bit further apart, had little windows cut out in them. Those are the open wire. All the power in feed lines that is lost in a form of heat. Now, you won't be able to put your hand on it and get burnt, but there is heat there. You can do it. Out at sea, when we were in the very north part of the Pacific, our antennas were getting iced up, feed lines were getting iced up. We would intentionally take them out of tune to build up heat in the hard line and in the coaxial line to melt the ice off of them, to get rid of it. Wasn't supposed to do it, but it's government property, you know. When it comes to coax, you've got the center conductor, the dielectric. The dielectric is that sort of clear plastic that covers that center conductor. And then you've got the shield. It's a braiding, or it can be a aluminum foil around it. Most of the time you'll find the braided wire. Some of the cable TV stuff will have foil. But basically you'll have the braided wire and then the jacket. The forward reflecting power is when you're measuring power, you measure the forward power going up to your antenna. Some of that antenna is bounced back from a mismatch, and that is reflected power. So here's a sort of a shot of the coaxial cable. If you're traveling along at home, it is on page 4-10. This here is the center conductor. It's a solid piece of wire in this instance. Down here on this one, you can't tell it very well, but it's a stranded wire. There is a difference. When you should use solid, you should use stranded. If you're on your base station antenna where the coax is not going to move or anything, use a solid center conductor. It works better than the stranded stuff does. But in your mobile, where you might be opening up your trunk lid, you know, moving the coax around, the coax is shaking on the back of the radio, use the stranded stuff in the center here. Designated as an A/U cable. Designates the slash stuff. Anyway, this is the outer jacket. Keeps moisture from getting in there, causing corrosion. This is the outer braid. This is braided wire, as you noticed on the examples in here. There was, there still is various qualities of coax. If you get a good quality coax like the Belden stuff, Belden is a brand name, it will be totally shielded with these braided wire. There was another radio supply company that sort of went out of business. It used to be very popular. I won't mention any names. Their coax could actually see this dielectric, the center plastic here, through these braided wires. They had very few. I guess they were just trying to save money on manufacturing. They didn't use all the braided wires like they should have.
What exactly is it shield? I mean, it serves as a conductor.
It is a conductor.
Shielding. What is it?
Actually, the braided conductor, yeah, part of the current goes up through the center, goes up, and comes back here. It's like a two-way street, if you want to visualize it like that. But they keep the shielded on here to make sure that other RF waves, especially inside the radio, doesn't get on this center conductor and start screwing with it. There was one little bitty tiny piece of coax, it's 174 on that board. That's the kind of coax that you use inside the radios. Because inside the radio, there's several oscillators going, and these oscillators are all oscillating at a frequency that could interfere with each other, with their harmonics and whatever. So the shield actually keeps any other signal from getting in on here and causing havoc. But it is a shield, and it's appropriately named for it. The good thing about the coax is, of course, is it's not affected by nearby materials. And what materials is stuff. If you've got a ladder line, an open wire line or something, you can't tie it next to the tower, your tower, to keep it from blowing in the wind. That stuff has got to be away from the tower. If you go back long enough where you see an antenna tower, they got the little standoffs to keep it away from the tower. Whereas coax, you can tape it right next to the tower, to keep it safe. The ladder line stuff, yeah, you had to keep it away from your house, the siding of your house, because it would affect it. There is a higher loss in coax than there are on the ladder line stuff, but the coax is just so much more convenient to work with. The air insulated hard line has the lowest loss. On that thing of coaxes, there's down at the bottom of it, there was some hard line, it said. The biggest one was, I think it was 7/8 inch, whatever it was. It had some white foam in it. The foam wasn't the dielectric. The foam was there to support the center conductor coming through it. The little holes in the foam, that was the dielectric. The little air bubbles inside was the dielectric. But the actual foam itself, it was just keeping the center conductor from touching the outer line. Open wire line. It is lighter, less expensive than coax, but you have to understand with this kind of stuff, you can't tape it to the tower. You can't have it running along downside your house. It's got to be out, away from everything. It has a lower loss than coax, so you lose less power on it. But the big problem of it is, it's always affected by all the nearby materials. And by materials, we're talking the tower and aluminum siding and right now. And it also requires an impedance matching equipment to match the antennas. This is an antenna tuner. On the back side, it's got these terminals here where I could hook in to these two wires. Hook them on the back here. For the regular coax coming down, I can hook into one of these depending on which antenna I'm hooked to. So that's why if you're having the open wires, you have to have a tuner. And the reason is because of the impedance. Found it. Whoops. What happened? Hey, Ben, we lost you.
Hey, Russ. Mama mentioned yours back years ago, it's called the antenna tuners, but
Yeah.
people understand that they can tune in the antenna, they're not really.
Yeah. Yeah, in fact, we go over that in one of the upcoming slides.
You know, when you were talking about skip earlier, it's been 20 years ago. It seems like radio technology's changed. But
Oh, my, yes.
I called in a traffic stop south of town here, and I could not get a hold of my, at that time, station was in Markville. And I ended up talking to somebody in South Carolina.
Wow.
They copied my radio traffic, and I was able to tell them who it was. They called District 12.
There we got it.
And told them where my traffic stop was. He called them on the phone.
Wow.
South Carolina, or North Carolina, one of the two. It's like the damn thing you ever heard. So we
Oh,
just got
yeah.
a call from North Carolina. So, sorry.
Yeah.
Make you
Go
ready
away.
for it.
Let's see. Let me go back and find out where we left off before we got. Okay, we're right there. And we need the matching equipment when you're using this open wire stuff. The characteristic impedance is the impedance or the opposition to the flow of the radio wave going through the feed line. Normally, it's expressed in ohms, like you got 50 ohm coax, right? And it depends on how the feed line is constructed and what materials are used. The coax is usually always 50 ohms. 75 ohm coax is used for cable TV stuff. Open wire line is 300, 450, and 600 ohms. And you got to match that, say 300 ohms with the twin lead stuff, into that 50 ohms of the radio. That is what this thing does. It matches that coax together, coax impedance with the radio. The standing wave ratio, basically it's just a comparison of the power that's being radiated out and the power that's being radiated back to the radio. You'll have this, it's called a mismatch, it's because most antennas are about 50 ohms, whereas if you got a 75 ohm coax on it, you'll have a mismatch. So it'll start reflecting things back. The forward and reflective waves, they create the standing wave on the line. And the standing wave is what we got to deal with the SWR. It's this ratio of the maximum of the standing wave to the minimum. So when your 100 watts goes up the coax, it hits the antenna. The antenna is not a perfect match, so some of that power comes zipping back down the coax into your radio. And this is not a good thing. You can measure, it's not a good thing because this power coming back goes into the radio the wrong way, and it creates heat on the finals, and it can burn up your finals. Sort of a layman's technology of how it gets there. You measure the SWR on an SWR bridge. If you've had a CB, you've probably seen an SWR meter. For CBs, it's about half this size, about this size here. You key up your antenna, the needle goes all the way up, you flip it to reflected, and it drops back down to zero, you hope, right? This particular one is for UHF and VHF. That's why there's more knobs on it here. The reflected power is reflected back at the transmitter, and it bounces back and forth this coax. Now, where the heat comes in at is in inertia. When this wave is coming back down, it's got to stop, then it's got to go back the other way. And when it stops, it's using up energy, creating heat, getting going again. So this SWR, the reflected power is going back and forth up there. And it essentially builds up enough heat down at the receiver that it can blow your final.
Now, is this, I'm going back to when I was a kid and we had CBs and the SWR meter.
Yeah.
We used it to adjust the length of the antenna. So,
Yeah.
So the antenna resistance and exactly what we're doing.
And we'll be getting into that, how you can find out if your antenna is too short, too long. In the third section of tonight, we'll get into that part. All this RF power that's coming out of your radio eventually is going to get it radiated out into the air, or it's going to be lost in the form of heat. One of the two ways. The higher the SWR, that means there's more reflections going back and forth, and less power being transmitted up, getting up into the antenna, where it's transmitted out in the air. Nothing is perfect. The perfect ratio, if your standing wave meter reads 1 or 1 to 1, that's perfect. You're supposed to say 1 to 1, but everyone just says 1. There's another, that's acceptable. No power reflected back. Up to a 2 to 1 or 2 standing wave is normal. You don't have to worry about it. You get your SWR down to a 2 and you're doing okay. You could mess with the antenna and get as low as possible, but you won't find that much difference in actual transmitting performance. The modern radios nowadays, they've got a protection circuit in it that senses it, that if the SWR is above a 2, it automatically starts cutting down the power. So there's less power going out, so there's less power coming back, so there's less heat to the final, so it protects the final. Above a 3 is considered high in most cases. When you're above a 3, that's when you got to start tuning. You have to make your antenna longer or shorter. Erratic SWR readings. If you got your meter on, you key your mic up, and the SWR meter is doing stuff like this. That means there's something wrong, physically wrong. You've got a bad connection, corrosion somewhere. It doesn't mean that it's out of tune. It means there's something actually wrong with the erratic reading. The high SWR can be corrected by tuning or adjusting the antenna. As the frequency goes up, the wavelength comes down. That's where you start tuning. You bring the antenna shorter, or you're making it longer to go into tune.
How does coaxial length fare into this? I mean, if you got exceptionally long coax, because your antenna is way the heck away from your transmitter,
okay,
then that's going to be greater resistance, right? So you have to
yes, no. Okay, length of coax. First of all, the longer the coax is, you will have more loss going up to the longer it is. And if the frequency, you start going up and up in the frequency, you'll actually get more loss. If you come from the CB world, you know that you got to have an 18-foot piece of coax to make your antenna work right. 18 feet, baloney. You can have 2 inches as long as it's 50 ohms. The reason 18 feet works so best is because these SWR meters are actually voltage standing wave ratios. They're just measuring the voltage, and it turns out that at 18 foot, you've got a peak voltage. That's you're a lower voltage. And that's why they have certain lengths of coax. You can have, the length of coax for SWR really doesn't mean a thing. Doesn't make any difference. But it will if you're using some of the cheaper type SWR meters. It might be harder to get a good reading, and that's it. And you do want to use the shortest coax as possible, because like I said, the longer the coax, the more loss you will get from the power getting up there. With the impedance matching equipment at the transmitter, this thing down here, you are not tuning the antenna with this thing. You are not tuning the coax with this thing. What you are doing is tuning the antenna system to the radio. You are tuning the combination of impedance of the antenna and the coax to the radio. You want the radio at 50 ohms, so you don't burn up the radio. So that's what you're doing with an antenna tuner. The standing wave is always going to be on there. It does not change on the SWR. The SWR will not change. But you're protecting the radio more than anything else with this thing here. And you're helping pump out, you're matching things up. better. So you will get a better transfer of power.
Is it kind of an adjustable resistor type thing?
In this thing, there's capacitors and coils. We're going to learn in this next section how a coil will make an antenna longer. A capacitor will make an antenna shorter. On a CB antenna, you got the loading coil down on the base of the trunk. That's a coil, and it electrically lengthens that 3-foot whip out to about 108 inches. That's all the loading coil does. It electrically lengthens it out. You can remember that too, because the coil, stretch out that coil of wire, it gets a lot longer. Yeah. Adjusting the SWR. That meter is inserted between the feed line and the transceiver. And I think there is a question about this. But you put the SWR meter right in here, you come out to the antenna, you make it longer or shorter until the SWR drops down. You want it under a 2. 1 is good, under a 2 is acceptable. You adjust the antenna for the minimum amount of reflected power. Some SWR meters, like this thing here, it reads forward power. No, it doesn't. This thing, this thing does. It will read your forward power on one of these needles coming up here, and it's two needles. The other needle will read your reflected power. So if you've got a good antenna match, the one needle will go up to full power output. The other needle will be low power reflected. And where they match, physically match, inside this meter here, there's a little red lines. And where they cross, you follow that little red line up to a number, and it will tell you if it's a 3 or a 4 or a 1 or a 2. You can take a closer look at this on the break, and you'll see what I'm talking about. Dummy loads. This is a dummy load, full of mineral oil. And it's got a resistor in here that's a 50 ohm resistor. It is a non-inductive resistor. We'll be learning about that in a little bit. But you use a dummy load when you're tuning your radio. You don't want to go in the air. You're going to be interfering with people. So you use this thing. This thing's good up to 1,000 watts because of the mineral oil in it. It's got a single resistor in here. It's about this long. It's a kit you put together. The dummy loads, they dissipate the signals in the feed line as heat. In other words, it's 100 watts that's coming through the coax into this thing. This is going to get hot. It'll get warm. It'll get warm. And like I said, it does, you can transmitter test without getting that signal out on the air and getting everybody mad at you. And it's helpful just in trouble with the antenna system. If you put this, your length of coax, you got a 50-foot piece of coax, hook your 50-foot piece of coax up here into the radio, and if everything works okay, it means your coax is good. If it doesn't work okay, it means you got trouble in your coax. So that's how you can kind of use a dummy load for testing. Okay, here's some questions. We're at T3A04 in the book, T3A04. What happens if antennas at the opposite end of a UHF-VHF line of sight are not using the same polarization? They're acting, if one antenna is like this, the other one is like this. And what happens? The signal will be significantly weaker. What type of wave carries radio signals between the transmitting stations? It's that electromagnetic wave. It's combined of the electrical lines of force, field of force, and the magnetic lines at right angles. It's the electromagnetic ones. Which of the following results from the fact that the skip signals refracted back from the ionosphere are elliptically polarized? It means that you can use any kind of antenna, a vertical or a horizontal antenna, to receive that signal. And that is because that signal is kind of, given at this routine coming around. So you can use either one. What property of the radio wave is to describe its polarization? It's the electric field. This is a very vertically polarized antenna because these driven element is vertical, and it's a vertically polarized wave because the electrostatic wave matches this one, whereas the magnetic waves are off at that angle, at a right angle. The two components of the radio wave is the electric and the magnetic wave. Some theory is, a lot of this stuff is theory. We can't see a radio wave, but we can study it, do the math on it. A lot of people say that the electrical wave, the magnetic wave going through the air that cuts through the antenna, the magnetic part of it gets these electrons moving. The static wave is the voltage that gives them the push to go, to do something. So that's how they work together to get a signal going. And remember, like I said here a couple weeks ago, the power of an incoming signal is like, one wafer of a little AAA battery cut into a million little slices. The change in dBs is the power of 3, remember? You go from 5 watts, you double it, 3 dB gain. If it was 10 watts to 20 watts, 3 dB gain. It's just the amount. Don't worry much about the wattage or anything. It's the actual amount of it. This one is a reduction. You're going from 12 watts down to 3 watts. Well, if you cut 12 in half, you go down to 6 watts. That's 1 minus 3 dB. Now, if you go from that 6 watts down to 3, that's another half, which is another 3 dB. So the total is a minus 6 dB. 3 dB. It's either double or half. The approximate change measured in decibels of a power increase from 20 to 200 watts. It's a 10 dB change. To show you a little bit how this all works, let me clean off this board a second. Okay, we're starting out with 20 watts, right? You double that, you go to 40 watts, 3 dB gain. You double this, 80 watts, another 3 dB gain. You double this, 160 watts, another 3 dB gain. You double this one, 320 watts, but 200 watts is right in here, right? So it's 3, 6, 9, and 1 more dB makes it 10 dB. And that's how you get it. That's how it works. Each time you double it, it's a 3 dB gain. A lot of guys don't understand it. They'll buy in between the S-meter readings, between like a 5 and a 6, there's 6 dBs gain between the S-meters, which means if you're throwing out 20 watts and you're throwing a guy an S5, to throw him an S6, you have to increase 20 watts, 6 dBs, up to 80 watts. That's how these dBs all work together in the powers of 3. The radio wave is made up of what type of energy? Electromagnetic, the electrostatic waves and the electromagnetic waves. The purpose of a dummy load, this thing right here. So you can test stuff on the air, test stuff off the air before you actually go on the air. And that is a big problem you'll have on the air. There'll be some guy from Peter One Island down at Antarctica transmitting, and you desperately want to talk to him, and there'll be another guy somewhere that wants to talk to him too. So what does he do? He goes on the air and starts tuning up stuff. And so he's blanketing everybody out, screwing up everybody. That's where he should have went to a dummy load, tuned up his radio on a dummy load, and then he should switch over to his antenna and try to do it. But you will see that a lot of times, guys tuning up on the air, and it is kind of aggravating. In general terms, what is the standing wave ratio? It is a measure of how well this load is matched to the transmission line. The load is the antenna. So it's basically how well this antenna is matched to the transmission line. And when we get into this next section after a short break here, we'll be showing you the different impedances of different types of antennas. The reading on a SWR meter that reads perfect match is a 1-to-1. Most solid-state radios reduce the power output as the SWR increases. Why do they do it? It's to protect the output amplifier transistors because of that heat buildup if there's a standing wave problem. An SWR of 4 means that it is out of tune and you're going to have to tune it. Anything above a 4, you've got to tune it. It's a mismatch. You can tune it by either shortening the antenna, lengthen the antenna, or put it through a tuner to do it. What happens to the power lost in the feed line? It's converted literally to heat. And there again, a 100-watt radio transmitter, if it didn't have any protection devices in it, and if it was shorted up by the antenna, you would have 100 watts dissipated in that coax. Have you ever touched a 100-watt light bulb? Same power. It would melt coax. What's a dummy load consist of? It's a non-inductive resistor. Some resistors have wire, made out of wire, wrapped wire, very precision. Not so much anymore, but back in the earlier days, they used wire to get really precision transistors. Well, that wire is a coil. And if you put current through a coil, it will make a magnetic field. So if I would have a inductive resistor in here, a wire-wound resistor in here, put power to it, it would start radiating out. Wouldn't be near as bad as going out on the air, but it would still radiate out and cause a lot of static. Types of antenna loading. Inserting an inductor into an antenna to make it electrically longer. Like this, coil of wire. Let's say you've got a lot that's 50 foot wide. You want to operate on 20 meters, which is about 64 foot. You need a 64 foot wide antenna, but your lot's only 50 wide, right? You can put this in it, and this will electrically lengthen out a shorter antenna. You might string up a 40 foot wire, put this in it, and that would electrically lengthen the whole thing out. So that's what these coils do. They electrically lengthen out the antenna wires. It's like the loading coil that's on the CB antenna. The whip comes up out of here. What is the gain of the antenna? It is the increase in signal strength when compared to a reference antenna. This reference antenna is a dipole antenna in free space. Dipole antenna, theoretical antenna. If this theoretical antenna could give the guy in Terre Haute an S5, and with your antenna, you could make him go up to an S6. That means he's had a 20 dB gain. So that's where you get that from. It's an increase in signal strength. That's the gain of the antenna, how well this antenna radiates out the power. It's important to have a low SWR, of course. We're in T9B, by the way. I should have warned you, some of these slides here, they jump from different test sections to different test sections here. So why is it important to have a low SWR? To reduce signal loss. Reduce the signal loss going in both directions, transmitting out and receiving in. It will affect it. But it will affect your transmitting out more than it coming in. The impedance in most coaxial cables used in radio installations, 50 ohms. Virtually everything is 50 ohms. The RG8 stuff, about as big as my thumb, 8 ohms. The gray RG8X, 50 ohms. RG58, the standard coax in mobile antenna systems, 50 ohms. And why is coaxial cable used for amateur radio other than the other systems? It's because it's easier to use. You just string it up. There's fewer special installation considerations. The special installation considerations are that the coax you can take next to the tower, window line you away from other metal. So it's easier to use. What happens as the frequency goes up in a coax cable, the losses increase. The smaller the cable, the more losses it will be when you get up into the UHF, VHF, and UHF bands. So that's why you want to use bigger coax when you're using VHF and UHF. What causes the erratic changes in SWR? This is where your needle is wiggling around quite a bit, and it's usually always a loose connection in the antenna or the feed line. And it's usually always, it could be a broken wire, soldering lug broke loose, it could be something like that. The type of coax feed line that has the lowest loss at VHF and UHF is that insulated hard line. Wherever it is, it's that bigger, thicker stuff. And like I said, the foam on the inside is just to hold the center conductor from touching the outer shield part. And it's the air-filled foam, the air in there, that's the actual air insulated, that's the actual line. 4B. Why don't we take about a 10-minute break?
Russell, you were talking about
erratic SWR. Good MFJ switch will do that.
Yeah. These things, are we on?
I need a second to take a breath, to keep me guessing with what you said. You're in my head. We're under pressure, we're sinking deep like stormy weather. Can't seem to breathe when you're with me. If you're gonna break me, I know I won't stay. I don't wanna wait here, you push me away. If you're gonna choose, you don't know what to do. I don't wanna lose you, but I don't wanna lose me too. So complicated, don't mess it up. Feeling frustrated, it ain't enough to fix a love. If you're gonna break me, I know I won't stay. I don't wanna wait here, you push me away. If you're gonna choose, you don't know what to do. I don't wanna lose you, but I don't wanna lose me too.
came and tucked your way into my heart. Oh, you look at me in ways I never loved. With you I know that this is all, so I don't need to take it slow. If you want me, then I believe that there's a simple remedy. We don't need no miracle, I think we've seen it all, just make the call. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. I'll come running over. We don't need no miracle, it's unconditional, just make the call, and I'll be yours. Don't need a miracle. Need a Oh, you open up a world behind the stars. Oh, you make me see the things I never saw. With you I know that this is all, so
This section is a little bit shorter than the other two, so we'll be getting out of here sometime tonight. This is all about practical antennas. We're going to just tell you about basic antennas here, just the very basics of them. The first one is the dipole antenna. It's probably the most commonly used HF antenna in the world. Its total wavelength is a half a wavelength. The usual construction is just two equal pieces of wire. If you're on 20 meters each, the feed line is connected right into the center of it, and the length in feet is usually just an estimated feet. You'll hear this thing of 468 over the frequency in megahertz. That's how you can determine the length of an antenna. You can remember 468 very simply. I'm going to etch it into your minds forever. Picture me up here as a cheerleader. Got a cute little skirt on, and I'm leading a cheer.
We're on the air, you know.
And I'm going 2, 4, 6, 8. Who appreciate, right? The 2 is a half wave, and then it's 468. You'll remember 468 for the rest of your life now. But that's is that it? But that's an easy little way to remember. It's 468. If you're operating on the 11 meter band or the 10 meter band, you'll divide 468 by 28 megahertz, and that will give you the approximate length.
In feet.
In feet, length in feet. The dipole antenna. This is if you're looking down at the antenna. You're up above it looking down at this wire going from that tree to that tree. You're going to have two lobes of it, one lobe and another major lobe, and then you'll have the null areas. When your antenna is pointed north and south, you're going to be transmitting the best east and west. That's your two main lobes. You're going north and south, going east and west. In this area of the world, most of our antennas, all of America is either east of us or west of us. So we want our strongest signals going east and west. Now, if you want to talk to or maybe South America, then you might make it east and west because your strongest ones will be going north and south. So it's broadside off the dipole antenna. They're very easy to make to wire. Here you go. You hook your coax up to this thing here. You hook one wire to that wire and the other to that wire, and you've got a dipole antenna. This particular one would be almost good on UHF frequencies, as short as it is. But if you would hook 32 foot of wire on here and 32 foot of wire going that way, you'd have a pretty good antenna on 40 meters. That's all it is. It's just the center conductor hooked to one wire, the grounded wire, the shield, hooked to the other wire. It doesn't make any difference if you're doing north and south. It doesn't make any difference where the center is located, as long as the entire antenna is always north and south. And I'll be off the broad sides of it. If it's a horizontally, it's just like these antennas here. It's horizontally, would be horizontally polarized. You want this because on the HF bands, virtually all the antennas are horizontally polarized. Virtually all of them are. The 3D pattern looks like a donut or a bagel, it says, and basically, if you could see the radio waves coming off this thing, they'd be like a big donut around here, a big donut going like this way, with that way and that way being the strongest. But this thing also radiates straight up and it radiates down.
That being said, if you look at the donut, the theoretical best height for it is what will make the donut near the ground.
Yeah, you do have, you try to get it up, for the best one, it's up above quarter wavelength. So if it's a 32 inches on this, or 32 feet, put up off the ground too. And that 32 foot off the ground, it will vary with the, gosh, the type of wire you're using and everything else.
Moisture in the ground, all kinds of stuff.
The ground plane. This is the ground plane antenna is what you have on your automobiles, right? You can also have them on your base stations, but a ground plane is the vertical antenna. It is half of the dipole antenna. The other half of the dipole antenna, this part here, is now the roof of your car. It takes the place of the other half of the dipole. It's a quarter wavelength, like I said, it's just half of this dipole, and act as ground plane, including the ground. In other words, this is a 2-meter dipole here. No, I don't think it'd be necessary. How about this? 2-meter vertical dipole. It's called a spike a lot of times. 19 inches for 2 meters. That's on the test. I don't know if it's on the test, but it's one of the test questions. It may be that that's one of the questions that gets asked. But it's 19 inches. So it's 19 inches up, and if it was a dipole, there'd be 19 inches going down. But if you put it on the metal roof of a car, metal roof like this, then this part all down here becomes the other half of this 19-inch dipole. 19 inches. The car roof, trunk, other metal surfaces. There are also some, if you make a ground plane antenna, a real cheap one, if you just want to make one, you want to get into the repeater, nothing else, you can take your coax, you can strip this outer conductor all the way off down to 19 inches. You pull that center conductor out of here, send it up, and you let the braided hang down. You've got a vertical dipole. That's simple of an antenna. Just a center wire going up and the shield going down. Makes a simple antenna. Very simple.
UHF conductor and a long piece of coat hanger
Yeah.
wire.
Any pieces of metal. It may get printed in QST. I hope it does. Last field day, I made a 15-meter dipole antenna. End to end, it was about 22 inches long. Each leg was 11 foot. 2 wires, you think 11 foot on each side, right? Not with me. I used 2, and on the other leg, and a steel cane hooked together with a little jumper. It was 22 feet long. That's all that it mattered. It was a conductor. I had a lot of contacts on 15 meters. 15 meters was really dead last field day because of the low sunspot cycles. A rubber duck antenna. A rubber duck antenna. After you've been in amateur radio for a while, you'll notice the rubber duck antenna is basically an air-cooled dummy load. These are the most inefficient antennas in the whole world. But what do you got to deal with? Huh? They're short, they're handy. They usually do the job. I can get into the repeater with this thing for 5, 6, 7 miles, you know. But if I would hook it up to an outside antenna, to an antenna on my car with an 18-foot quarter wave spike, then I could double that range easily. Convenient size. It's basically a coil of wire is what this is in here. It's just a coil of wire. It's a very It's a loading coil that's the entire antenna. It doesn't have the little spike coming up out of it. When I do use this thing, a lot of people don't realize too that the ground plane, this is the vertical, the antenna and my arm and my body is the ground plane. Most humans' bodies are pretty well resonant to 2 meters because of our height. The small size does compromise performance. Yes, sir.
Kind of like on the old antenna TV, like if you actually grab the whole.
Maximize range. Like I say, you'll be watching this in movies from now on too. You'll see somebody talking like this on an antenna and you go, idiot, doesn't know how to use a handy-talkie radio. It happens. They just don't realize how important it is to keep these antennas both vertically or both horizontally. They have to keep them the same each way. Of course, these things does not work well inside an automobile because it's enclosed in the metal part of the car. And you can literally just stick it out the window. Hopefully you're not driving, but if you just stick it out the window, it will vastly improve the performance of it, just getting it outside the car. For mobile use, of course, they do say replace rubber duck with a mount or a permanent magnet. Nowadays, most of the walkie-talkies, handy-talkies, whatever you want to call them, these little things here are called SMA mounts. The SMA female, the jack here is an SMA male. You have to get an adapter. They're on that board going around with, oh, wait a minute, let me get this thing going around too. You get on this right here, this is an SMA female. This thing here would screw in to this radio, and then a regular coax would screw in here. So you could hook up a regular coax. These are little adapters. By the way, when you go to a Hamfest and stuff, when you get your handy-talkie, you'll know immediately if it's a B and C connector, the old style, or if it's the new SMA style. You'll know immediately because you have to screw it in there. When you go to a Hamfest, buy an adapter that will adapt whatever mount it is, whether it's B and C or SMA, to where it will go into a regular PL259. Screws on. Yeah. Mm-hmm.
One thing you gotta watch out for, some radios use different, I know on Yaesus they use one type of SMA and those things use another one.
You mean the female, the gender?
I think so, but
yeah. Yeah, this particular one, this is a Yaesu. It's got the male here. You know the difference between a male and a female? Okay, yeah. The male's got the thing sticking out, and the female is what you stick that little thing into. Okay? Okay, some of them are just the opposite. It just depends on the manufacturer which way they want to go. And motor, yeah. The half-wave dipole, recommend that you start out with 490, because if you start out with 490 in the equation, you'll be extra long. It's easier to cut off and make it shorter than it is to make it longer. Ground plane construction. It is usually in feet. It is 234, half of 468, because the ground plane is a quarter wave, half of a half wave, right? And there again, it's often short. You want to start out a little bit long so you can cut it down to bring it into tune. The thickness of the rod makes it, affects the calculated ring. If you would put up a really thick copper pipe up into the air, you would have a lower SWR over a wide range of frequencies, as opposed to if you just used a 14 gauge wire. So the bigger the diameter of the stuff, the flatter the SWR is. And you can use it over a bunch of frequencies without having to retune it. The vertical antennas, they are omnidirectional. They go around in all directions. One of the most popular homemade antennas for VHF and UHF is a sort of a J-pole. You can go on the internet and just type in UHF, VHF, ham antennas. And there's all sorts of guides that shows you exactly how to make these antennas. They work quite well. I went to Menards and bought aluminum rods, some aluminum angle iron, stuff like that. And I made a UHF VHF omnidirectional vertical antenna for my house. And I have talked to, gosh, I've talked up to Taylorville on it. I can make it to Greenville, a really long ways on that antenna, and it's all homemade. So you don't have to go out and buy these expensive antennas. You can make them yourself. And the internet has a wealth of information on building antennas. You mount the mobile whips in the center of the roof or in the trunk for best coverage. That's because you want the center of the ground plane, the entire metal. You want it right in the center. So the signal goes out well in all directions. You should consider lengthening this quarter wave up to a 5/8. This is a quarter wave UHF. This is a quarter wave 2 meter. If you lengthen this quarter wave out to a 5/8 wavelength, you will get a lot better signal performance because it will keep the signal down to the earth better. So the signal will go a lot further. And it's all mathematical to get to that 5/8 wave. Where were we at here? Nope, going the wrong way. 5/8 wave. I'll try to do it on here. A quarter wave. Whoops. I must have. Whoa.
You go on the laptop, you should be able to scroll.
Ground plane, here we go. 5/8 wave. A vertical. The verticals are 19 inches, right? For 2 meters, 19 inches. It's a quarter wave. Multiply by 4, the full wave comes up to 76 inches for a full wave. Now you want to build a 5/8 wave. 7, 6, 64? Be 30, yeah. What is it? 8 times 8 is 64. 8 times 9 be 72. Around 70. And then multiply that times 5 of the 5/8 wave, and they'll tell you how long that whip's supposed to be. Need a calculator. I haven't done math like that in a long time.
35 inches, give or take.
35? Okay.
Well, wouldn't 5/8 0.625?
625. Yeah, about that.
So 76 times 0.625 is 47 and a half.
Yeah. Yeah. Mm-hmm.
Now, you kind of touched on it, but you didn't touch on it. The thing to remember when you're picking a frequency to tune an antenna to, that antenna is going to be resonant at that frequency.
Yeah.
Truly resonant. So as you go up and down a band, you are going to see your SWR vary a little bit.
Yeah.
On VHF, UHF, it ain't that bad.
It's not that bad.
What you normally do is you pick the center of the band you want to use, and you cut to that frequency in the center of the band. Otherwise, on HF, you'll see a little more variance. You'll have to nudge the tuner a little bit, when you get to that point.
The directional beam antennas, of course, like we already know, the beam antenna points it all in one direction. The gain it gives you increases your range, of course. Reduces reception in unwanted directions. If you've got this antenna pointed east, it will reduce all the stuff coming in from the sides and from the rear. In front of the station. The directional characteristics, like we just discussed a little while ago, it is the same for receiving and transmitting. So when you've got your antenna pointed that direction, you will receive really well all the signals coming from that direction, and you will be able to transmit really well all the signals going that direction. This is a beam antenna, what it might look like up on a tower. This thing right here, that's a mast coming out of the top of your tower. And then these things are the concentrate all your VHF and VHF to avoid multipass and to bypass obstructions. And the way you do that is if you're in a big town or something and you're trying to get a repeater there, but there is a building in the way, this way and bounce it off a different building to bounce it into the repeater. The horizontal elements are used for sideband and SSB. In UHF and VHF, if you're going to use Morse code, CW, or if you're going to do sideband where you can talk a greater distance, you want your antenna to be horizontal. And if you're on the HF bands, you'll want it horizontal. Other modes, like if you're just getting into the repeaters or just talking local, then it will be vertical. Microwave frequencies, above 1 gigs. You've all seen these dishes, antennas from Dish Network and all this stuff. Very short wavelength. I'm talking very short wavelength here. Very high gain. And it's relatively small in size. This is one of the older big 10-foot dishes down to like the 18, 20-inch dishes. Practical feed lines. There's the coax cables. The larger cables have the lower loss. You use the cables you can. The loss is measured in dB per foot. What this means is when you buy a chunk of coax, it will have its specs written on it. And it will say a 100-foot length of this at 30 megacycles will have a 3 dB loss, okay? That means if you're putting out 100 watts into this cable at 30 megahertz, when it comes out the other end, it will cut your power in half. You'll only have about 50 watts coming out. So there's that 3 dB again, indicating a double or a having power.
Generally have a range of losses per frequency.
Yeah, they won't just have one frequency. It'll be, yeah, it'll give you a whole range. So you'll know what you're going to be using this coax for, whether it's HF or UHF. Range there, how many dBs it is. But there again, the loss does increase with frequencies. As the frequency goes up, you're going to be losing more power. You want to keep the water out of it. Water causes corrosion is resistance. All right, to protect the jacket from cuts and cracks. So you want to get a good coax jacket on it. Some of the cable is UV rated. The ultraviolet rays coming from the sun, the same rays that are ionizing the ionosphere up there, also can cause a little deterioration of the coax where moisture can seep into it. RG174, that's that very small coax that you saw on the board. That's used inside of radios. The RG58, it's 0.2 inches. That's almost a quarter of an inch. A quarter of an inch is 0.25, right? Well, the 58 is just under a quarter of an inch. And it's very lossy at UHF and VHF. But on mobile antennas, you can get by with it because it's such a short length of coax. There's not that much loss. RG8X, that's the gray stuff. And it is a quarter of an inch outside diameter. And it's good up through low VHF. Although I've used it at home on UHF, and I have pretty good results with it, with the UHF. The RG8, it's also called RG213. There's also 99s. There's a whole bunch of different kinds of RG8 style of coax. It's almost a half an inch in diameter, and it's used all the way up through UHF, from down at HF all the way up to UHF. The hard lines. 3 different sizes of hard lines. And it's good. That stuff is good up through the microwave frequencies. It's good to way up, high in frequency. Most coax is 50 ohms. The regular coax is 50 ohms. The 75 ohm stuff there again is mostly cable TV. The coaxial connectors. There's a picture of all the connectors, and there's various forms of them on that board we sent around here. Some of the ones you'll be using for UHF. It's the SO239 is the female. The PL259 is the male, and it's used on low UHF and down. BNC connectors, a lot of test equipment, and a lot of the earlier walkie-talkies used the BNC connector for the antenna thing. The N connector is very good on the UHF frequencies. It's also weatherproof, and it's also a bear to put on. The SMAs should never have been invented, but they were. The SMA mount is this little bitty one, like these things here. And believe me, to put these things on, I can't do it because of my eyesight. This is very small stuff. You crimp them on. It's not a lot of fun. So basically, the only SMAs you're going to run in contact with is the ones on these antennas and the adapters that you screw in here, the adapters that you screw on to regular coax connectors. Actually finding like a coax wire 25 foot long with SMAs on both ends, nah, don't have to worry about that. boy, I hit something there. Oh, okay. The F fitting is the cable TV fittings. You guys won't be using that in amateur radio. Installing the coax connector, soldering is the traditional way, and you want to make sure you use rosin core solder. You can't use acid core solder like you use on plumbing in your house. The wires are so thin that that acid will actually eat up the wires, so use a rosin core. You want to avoid cold solder joints. That's when you're putting solder on a wire and you just don't get it hot enough, it doesn't run. It'll have a real dull gray look to it. Crimp connectors. This is a crimp connector, factory put on connector. No soldering, it's all crimped together. Does quite a good job. You do kind of have to watch it though, because sometimes physically they don't make a good electrical connection. Not as good as soldering. And use how to waterproofing connectors. They got to be waterproofed if you're working outdoors, and it's simple to waterproof them. Ends are waterproof, but they should be protected anyway. Good quality electrical tape is all you need. You screw the coax up to the antenna, you take your electrical tape, tape it up around there. Mine at home, I taped it up around there. I smeared some silicone sealant on the outside of the tape, and then let it dry, and then I put more tape around it. I mean, there's no moisture going to get into my coax. Coaxes require special connectors and techniques to waterproof. Some of these air core coaxial cables, they'll put like helium into it to keep pressure into it. They'll put dry air into them to keep the moisture from migrating inside. Practical feed lines. These are the open wire lines. The ladder lines, that kind of stuff. They're low loss, but they've got two main problems. First of all, you can't put them next to something. And the second time is they will break. They usually use solid wire in those things. And like any solid wire, the constant flexing in the wind will break them after a while. Snow and ice and rain and all that stuff, they get on those lines and it will affect your standing wave. The lower the loss in the coax generally, it's a lower loss than coax generally, the open wire lines are. And the higher impedance is the downfall, because with the higher impedance of the open wire lines, you have to use a tuner. And we're going to wrap this up by talking about these 4 meters. The watt meter. Most watt meters are directional. They will read the power going out and the power coming back in. They will read the forward and reflected power. They use a sensing element to sense which way it's coming from. And then the SWR is computed from the power values. In other words, you'll have a line on it, maybe a little graph, something as simple as a graph saying, if you've got 40 watts forward and 2 watts reflected, your SWR is a 2. An SWR meter, these are the ones that you've seen a lot of with the CBers. Simple little meter and adjustment. It does read the voltage standing wave ratio. It's usually installed there at the transmitter. The tuners, they don't really tune the antenna. What the antenna does, it transforms the antenna impedance, the antenna system impedance, to the radio. It takes the impedance of the antenna, the impedance of the coax, or open wire line, and it matches that total impedance to that 50 ohm impedance of the transmitter. And of course, you want to get it down to 1-to-1. The antenna feed point impedance is not changed up at the top. If it's a mismatch up there, it's going to stay a mismatch even if you got a tuner. The SWR and the feed line is going to stay the same. What's going to change is just that impedance, the collective impedance down at the radio. You transmit a low power signal. With this antenna analyzer, it's actually a little transmitter. Little bitty weak power comes out of the top of this thing that sends it up to the antenna, and then I can read it on the meter, the frequency of it and the strength and all that stuff. You usually can leave the SWR meter in line all the time, so you can just keep an eye on things. You don't have to, but usually they just do. The antenna analyzers, these things are a beautiful little job. There's one here, and Doug brought his over there. Doug's will go up to UHF. This one just goes up to VHF. Like I said, this is a really old one, but it's an old workhorse. And with this thing here, I can read the frequency, I can read the forward power, reflected power, impedance, all that kind of stuff. It's really handy to have. Unless you're really into building antennas, if you really like building antennas, you'll want to get one of these. But if you just like getting on the radio and talking, you just need an SWR meter. You'll get by with that. Of course, they're available HF through UHF up to microwave. And it is very handy for adjusting and troubleshooting the antennas. You'll know if you got to lengthen or shorten it by just reading it. And now the questions, and then we'll be done. What antenna polarization is normally used for long distance weak signals CW and SSB on VHF and UHF? Horizontal. You also use horizontal on HF, but it's horizontal. When using a directional antenna, how might your station be able to access a distant repeater if there are obstructions in the path? You can try to bounce your signal off of something. You're trying to find a path that will reflect your signal and bounce it back in. And by that I mean you can, if you see a water tower, you could bounce your signal off the water tower and reflect it back into the repeater. Stuff like that. On one fox hunt we had, a guy had a directional antenna. He had it pointed at one of these water towers here in town. Had it up on high power. When we were all looking for him, right? When we were all looking for him, we were getting a really strong signal off that water tower, or the direction of the water tower. We were headed for the water tower to find him. When we got to the water tower, we took new readings and found out, wait a minute, he's not around here, he's somewhere else. But they will reflect off of buildings and water towers and stuff. The proper location for the external SWR meter is right outside the radio. Some radios will have built-in SWR meters. Can be used to determine if an antenna is resident at the desired operating frequency, an analyzer. If I'm operating on 14 megacycles again on the 20 meter band, I will tune this thing to that same frequency, put the antenna coax on it, and then I can find out if it's in tune. I can adjust it without having to go on the air. But I can go right to the frequency that I'm operating on to use that radio and get it tuned. Other than an SWR meter, what can you learn to see if the feed line is properly matched? You can use a directional watt meter because you'll know that you want all the power going out. If you're a 100 watt radio, you want forward power 90 watts, reflected power 10 watts. And you want to get forward power as much as possible. What is the following most common cause of failure in coaxial cables? As a technician, I will argue with this: moisture contamination. In mobile antennas, it's broken wires, smashed coax. Very seldom did I ever run into, in the 30 years I was doing it, very seldom did I run into moisture in the coaxes. Now on a base unit, on a base radio, where you've got the antenna up out in the weather, yeah, you can get moisture in it if you haven't got that connector, really sealed tight, and if the outer conductor starts leaking. And why should this outer conductor be resistant to ultraviolet light? Because it can damage the jacket and allow water to get in. Shrink the jacket. Sometimes you pull the jacket away from the connector itself, and there you can see the braided wire, so it'll get in that way. Disadvantage of an air coil coaxial cable when compared to the foam or dielectric types: it requires special techniques to prevent water absorption. You got to fill that thing up with air pressure or some kind of inert chemical, gas, to keep the water from getting into it. And so it's a lot more work. And of course, you got to have the special connectors too to put on. The type of solder: rosin core solder, definitely. The characteristic of a cold solder joint: on that going around, I had two PL259s. One of them had a nice, good solder connection. It was shiny, and the other one was kind of a dull ball on it. That's the cold solder joint. The dull or grainy surface. What is a beam antenna? An antenna that concentrates the signal in one direction. These sound really easy questions to you now. After you've been in this book, and every week you should be going over these questions and answers. Read the question and then read the correct answer. Forget about the wrong answers. Read the correct answers only. If you do get a question on the test, use your first guess, and that's usually the correct one because you've seen it so many times. A simple dipole oriented parallel to the Earth It is a horizontally polarized antenna, right? What is the disadvantage of the rubber duck antenna on most handheld radios? As compared to a full-size quarter wave, it does not transmit or receive effectively. When you get a quarter wave antenna for your car or something, you will notice an amazing difference between performance when you go from the rubber duck to a regular, like quarter wave spike or a 5/8 wave.
These antennas here are mostly stock, but you can buy another antenna that screws on. They're quarter wave. The 5/8 wave. Chip and UHF, but I could sit here in my house in Alabama and talk in here with it. And do that when we have power outages. This won't cut it. So I can put another antenna on, you can buy them, and it'll screw right out here.
A lot better performance, yeah. How would you change a dipole antenna to make it resonant on a higher frequency? You make it shorter. As the frequency goes up, the length goes down. You shorten it. What type of antennas are quads, Yagis? Yagi is a Japanese guy that really came up with the idea. This is Yagi antenna, style of antenna. He came up with it. And the dish, they are all directional antennas. The disadvantage of using a VHF transceiver with this integral antenna inside a vehicle. What they're asking is, what is the disadvantage of using a walkie-talkie with a rubber duck? They're using these big words for that's basically what they're saying. And in fact, the signal will not propagate well due to the shielding effect of the vehicle. The approximate length in inches of a quarter wave at 146. It's 19 inches. You need to remember this. You'll be using this figure a lot when you make your antennas and fool around with antennas. You'll be able to look at an antenna, if it's 18 inches long, you go, that's a VHF antenna. It's about 5 inches long, you'll say, well, that's a UHF antenna. 19 inches is for 2 meters. The 6-meter antenna dipole is 112 inches long. And there again, if you divide 50, which is a 6-meter band, approximately 50, into that 246 or 468, all that kind of stuff, you'll come up with 112 inches. Which direction does a half-wave dipole antenna radiate the strongest signal? You got a half-wave dipole, it's broadside to the antenna. Good reason to use a properly mounted 5/8 wave antenna for UHF and VHF is because a 5/8 wave will hold that signal down to the ground better, and you'll get a lot more distance than you will with a quarter wave. The major function of an antenna tuner, called an antenna coupler, it matches the antenna system impedance. It doesn't match the antenna, it doesn't match the coax, it's the whole system. It matches the antenna system impedance to the transceiver output impedance. Virtually all transceivers are 50 ohm impedance outputs. Which connectors are suitable for frequencies above 400 megahertz? And that's the N style of connector. From the outside looking at it, there's not that much difference from a PL259, but if you'll actually look at the inside part of the plug, you'll see that there's a big difference between them. What is true of PL259 connectors? They are commonly used at HF frequencies and also commonly used on VHF frequencies too. It's a very common connector, the PL259. Why should coax connectors be exposed to weather, be sealed against water? Is to prevent that water from getting inside and preventing an increase in line loss. It makes the copper corrode, more resistance in the copper, more resistance to the flow of current, buildup of heat. There you go. The difference in 58 and 8 has a lot less loss given any particular frequency. No matter what frequency you're using the two on, 58 will be a lot less. It's bigger wires. The current can flow down easier because there's more copper. Next week, ta-da, 9:30. Next week we'll be going over 5, section 5. So I want you to read 5. It starts on 15-1. If I can get my fingers to work right. It is all about amateur radio equipment. And we'll be talking about different kinds of radio equipment. Byron, can you bring in your linear? next week, possibly. If you can, I'd appreciate it, because I've seen this linear he's building, and it is really a work of art. And I'd like just to see what this guy is building. It's a beautiful, beautiful linear. So anyway, this week, read chapter 5, and be going to the back of the book constantly and going over these questions. Start on T1 if you have to, and read their question and read the right answer only. And just constantly go over it. Also, it's a really good idea too to go online and take these practice tests. You will be amazed how much that will really make these questions stick into your mind when you're taking those tests. Right now, if you would go online and take a test, you would probably come pretty close to passing the test, because we've already went over about half the questions, and like a lot of these questions are simple common knowledge stuff that if you think about it a little bit, you can get the right answer. So get online, take these tests. QRZ.com has got them, QRZ. In ham radio work, we never say the letter Z, we always say Z. It's always been done that way, and we're going to do it that way forever. It's QRZ.com, and then ARRL also has some practice exams. They'll really help you remember the questions and answers. And that is it.
Does anyone have any questions?
Any questions?
Yeah.
If not, if you want to hang around and look at some of this stuff up here, feel free to. That's why we brought it.